All right, so is this a first law problem or a second law problem? How do you know? Yeah, they tell you it's accelerating. Pretty easy to determine on this one. So we're going to start as a second law problem. All right, that's step one. So step two is draw a free body diagram. You should probably be taking a little more care. When I walked around, I saw a few of you, they're messy. And messy is going to make these harder. Grab a ruler, be patient, take your time. Um, would anybody like to venture one of the forces that are probably acting in this problem? All right, so sounds like we're saying the weight. And how do I draw the weight? Straight down. You have access to a ruler, consider using it. But I'll draw an arrow straight down to represent the weight of the object. Is there any other forces acting on the object? Go ahead. Yeah, normal force from the ramp. I don't get a choice on how to draw this, but the moment there was a surface in contact with another surface, we had a normal force. To draw that, it has to be perpendicular to the surface in contact. So that looks perpendicular to me, as close as I can make it at least. These aren't arbitrary arrows I'm just throwing around. I'm trying to be careful and measured. Now, we know the system's not balanced. However, I believe there's probably another force. Why do I think there's another force? What's that? Um, that's not why I think there's another force. Go ahead.
Because it's sliding against the surface.
True, but it could be frictionless. I think there's another force because they're asking me to find a different force than I've listed already, right? I mean, question number one says, find the size of the frictional force. I think there's got to be a frictional force then. I mean, literally that ridiculously easy, I think. But drawing friction, it does come with some conditions. It has to oppose the direction of motion. Do we know the direction of motion? Yes. So I have to draw it in the opposite direction of the motion of the box. So it's got to be up the ramp. That's not arbitrary. And as I walked around, I saw a lot of people who were drawing stuff like this. That's not going to serve you very well. Make it careful, make it measured. It has to be perpendicular to the normal force. So do your best to make it look perpendicular to the normal force. Because later on, you're going to have to apply a coordinate system to this mess, and the cleaner it is, the better it will be for you. Now, your next job is to do just that, apply a coordinate system. And you have two rules for applying the coordinate system. The first rule is to line it up with the direction of the acceleration, and the second rule is to try and line it up with as many forces as possible. Which of those rules are we going to use today? We're going to have to use the acceleration one because it is accelerating. So I want to line it up in the direction of the acceleration. This is not it. The direction of the acceleration is down the ramp, so I'm going to turn this so that's lined up with the direction of the acceleration, down the ramp. And that means I'm going to make this my positive x direction. I would always encourage you to make the direction of the acceleration positive if you can. It will help you out later. And I'm going to make this the positive y direction. Do I have any forces that are off-axis forces? Yeah, I do. I have the weight is off-axis. So because the weight's off-axis, I'm going to have to resolve the weight into its components. So we're still right here, 3, coordinate system and resolution of vectors. I have to put that 40 degrees someplace, and that 40 degrees goes right there. And I will break up the weight into 2 components. This one is going to be the weight cosine 40, and this is the weight sine 40. All right, we're down to step 4, which is apply Newton's laws. we said it was a second law problem, but we lined up the acceleration to be in the direction of the positive x direction, which means the second law goes directly to the x direction of the problem. The y direction, by extension, has to be 0. This is why you line up your coordinate system with one dimension, so the other dimension will net force to 0. Because if you don't do it this way, then it's going to be accelerating in both dimensions, and you won't know how much. So I would strongly encourage you to always make sure that if it's accelerating, you line up just one dimension with the acceleration. Now we just put the forces where they go. For example, the x one, I think this is in the x direction and this is in the x direction. Those are the only two that are in the x direction. One's pointing towards the positive and one's pointing towards the negative, so it looks like I'll get W sine 40 minus friction equals MA. The other one looks like this and this, right? One up and one down. So normal minus W cosine 40 equals 0. All Newton's laws can do for you are generate relationships. These are our two relationships. So now that we're here, can we answer our question? Can we find the size of the frictional force? Can we find the ratio of friction to normal? I think we can. We'll need to know what W is, but we already know what W is. W is mg. We know G is going to be 10. M's given to us. It was 2 kilograms. So let's put this together. Mg sine 40 minus friction equals MA. 2 times 10 times the sine of 40 minus friction equals 2 times 3. Not terrible. This is where you get 6.9 newtons. Now to get the ratio of friction to normal force, you are going to have to solve for the normal force. That'll be right here. Normal force equals mg cosine 40. I think that comes out to like 15 point something. Is it like 15.4, 3? So you find the ratio, 0.45. This is a last week problem. So let's make it a this week problem, okay? Now, I've got to add something to this today, so we are. This ratio has a name, and it's called the coefficient of friction. The coefficient of friction is a term that refers to how rough or smooth a surface is. Now, there's some notes to take here, so let me be kind of clear with you. The coefficient of friction is not a complicated idea. It's a complicated word, though. Coefficient of friction sounds way bigger deal than it actually is. You should know from algebra, coefficient just means a number in front of a number. Right? So that's from your algebra class. In this case, the coefficient of friction tells you how much friction you get for your normal force. Rougher surfaces produce more friction. Smoother surfaces produce less friction. In fact, that's such a deal that those are considered vocabulary words, rough and smooth. If a problem describes a surface as smooth, they're describing it as being nearly friction-free. If they describe it as rough, it means you have to assume there's an appreciable amount of friction. So rough and smooth are vocabulary words for your test. If they say in the problem that you're dealing with a smooth surface, you can assume friction is 0. If they say you're dealing with a rough surface, you have to take into account the frictional force. Okay, so those are vocabulary words. It's the best way I can describe it, rough and smooth. Now, with that being said, the coefficient of friction is a way of measuring the size of the frictional force. And there's just a couple of details here I think you really should write down. The first is there is no friction without normal force. Right? You have to have a normal force for there to be friction. The normal force tells you that the surfaces are in contact. So there's no friction without the normal force. Repeated 4 times. And I'm interested in who decides that that's important or not important. There, I think message has been received. The next thing I want to point out is that friction is a percentage of the normal force. Right? That's why this ratio exists. It's a percentage of the normal force. So it's how much friction you're going to get from your normal force. Rougher surfaces will produce more friction. Smoother surfaces produce less. This percentage kind of tells you what you're going to get. So the coefficient of friction is usually a number between 0 and 1. And it's unitless because it's just a ratio. Herein lies the true problem. The symbol we use for the coefficient of friction is a little off-putting for folks because we do use a Greek symbol for it. We use the Greek letter mu for the coefficient of friction. This is what it looks like when I draw it, so consider like a P or a G. It's going to have a little hangy down part, but the size of the letter should be about, that's a capital N, that's about how big it should be. If it's typed, often it looks like that with that front line being straight. You're going to need to be able to recognize it on the test, and you're going to need to be able to write it in such a way that I can recognize it when you turn in your test. Does that make sense? There are 2 kinds of frictional force. So let's talk a little bit about them. There's static friction, and what we just looked at, which is kinetic friction. Kinetic friction is also called sliding friction because the surfaces have to be moving. So in this situation, they're going to have to be moving. Doesn't mean accelerating. It just means moving. So it can be constant velocity or accelerating. That's going to be sliding friction. And sliding friction is exactly what we just described. It's going to be a coefficient times the normal force. That tells you how much friction you get for your normal force. But again, kinetic friction talks about a situation in which one surface is sliding past another. So it's got to be moving for there to be kinetic friction. Static friction is also called starting friction. This is something you have to overcome in order to get something to start moving. So in this case, the object is going to be stationary or at rest. Right? The friction is holding it in place. This one's going to be a little bit different because you have to think a little bit about this. Let me tell you what I mean. Inequality lets us know that the frictional force in this case can be any value up to and including some maximum. But after that, you break static friction and kinetic friction takes over. So the static friction is an inequality. My experience with students is that you're not used to dealing with inequalities, especially in situations where you're generating relationships. So we're going to practice, but I want you to hear this phrase a lot. Whenever you have an inequality and you have to use it as part of your function, always substitute into the inequality. That preserves the inequality as part of your problem. You see, this doesn't say it's equal, right? It says that it's less than or equal. So it's any number of values up to some maximum. So whenever you're dealing with static friction, you have to use the inequality, and you have to learn how to substitute into the inequality. Well, we're going to do an example right now for you to do. We're going to do the book example, right? So here's the deal. I want to find out what angles are safe for the calculator. So consider, and this is the opening situation from the beginning of class today. So consider I have the book, just like before. And I'm going to put the calculator on the book. And let's say the calculator is 0.5 kilograms. And let's say that there's a coefficient of static friction of 0.8 between the calculator and the book. And we're going to start to tip the book upwards. What is the maximum angle I can have the book before I break static friction? Now, this problem is a little different than what we started with at the beginning of class, but you do notice that we're going to be able to use the bones of the other problem pretty easily, right? Like, I don't think we have to reinvent the wheel here. We can go back to that same drawing we started at the beginning of class. That all good for you guys? But is this a first law problem or a second law problem? This is a first law problem. Any static frictional force problem is going to be, why I put the S there, is going to be a first law problem. Yep. Friction. If the object is sliding with a constant speed, you make that a first law problem. If it's accelerating, then it's a second law problem. Yeah, because it was accelerating. But I could have done the same problem, just said it was sliding down the ramp at a constant speed. Right. Would have been a first law problem. Now, again, we're just going to reuse a lot of what we did with our first question. So I don't feel the need to go through all the same kind of precision and discussion as we did before. So we'll have a downward force that represents gravity. We're going to have a normal force that's perpendicular to the surface. And we're going to have a frictional force that is parallel to the surface. And we're going to choose the same kind of coordinate system, so none of this part's changing. So there we go. I'm going to choose this to be the positive x direction and this to be the positive y direction. Again, we're doing all the same kinds of things we've already done. This will be theta. So just reusing what we already have because we did this portion already before. So this takes us through our free body diagram. We have one off-axis force. We're going to have to break it up into components. And one component is down the ramp, and one component is into the ramp. Again, our force concept model generates relationships. It doesn't solve your problem. It generates relationships. So that's what we're doing when we're using the force concept model. Is we're walking through and getting to a point where we can say net force in the x direction equals 0, net force in the y direction equals 0. We've generated a relationship in the x direction that says W sine theta minus friction equals 0. And we've generated a relationship in the y direction that says normal force minus W cosine theta equals 0. All right, the force concept model just generates relationships. So we have generated the two relationships, one for the x and one for the y. And now we can try and focus on seeing if there's a way to use this to solve our problem. So I will point out weight is equal to mg. That's a substitution we can do. So if I do that, I'll get mg sine theta equals friction. And normal force equals mg cosine theta. But I'm no closer to solving for theta. Right? Our question is, what is the maximum value we can have for theta before the book slides? And I can't solve either one of these. I mean, I know the mass of the book is 0.5. I know g, but I don't know theta, and I don't know friction. I'm trying to find it. But I have more information. I have this coefficient here. So obviously, I'm going to be working in the coefficient of friction. And whenever you have a coefficient of friction, you're going to have one of your two versions of friction. In this case, we have static friction, which has to be less than or equal to mu times the normal force. Now, this is an inequality. So whenever you're dealing with an inequality, I would encourage you to do it the way I'm about to describe, which is substitute into your inequality. That preserves the inequality. If you substitute out of it, it's not equal. So like I can't take this and put it here for friction, because friction doesn't equal that. Friction is any value up to and including that. But if I substitute in the other direction, meaning I take this and put it into friction, then I'm preserving my inequality. So that's what I'm going to do. I'm going to substitute into the equation that has the inequality. That will preserve the inequality, and I'll know how to deal with the inequality then later. So I'm going to do the substitutions as you see them. mg sine theta less than or equal to mu s times mg cosine theta. Well, now I think there's a method to solve for theta. I'll first point out that I can cancel out the m on both sides. Do you guys see that? So I can divide by that as long as it's not 0. I can also divide by g on both sides as long as it's not 0. Now I'm left with sine theta is less than or equal to mu s cosine theta. Do you know a way that we can solve this for theta? Go ahead. Sure. That'll do it. So now the left side is tangent theta is less than or equal to mu s. Now, we're not quite done. We still need to figure out what theta is, but it tells me that theta has to be less than or equal to the inverse tangent of 0.8. Right? Mu s was 0.8 at the beginning of the problem. But it also tells me something clear, and I want to make sure you see this. It tells me what side of this angle I have to be on, right? We preserve the inequality. So it says clearly that I need to keep the angle equal to or less than whatever this angle happens to be. Let's see, it's 0.8. I got 39 degrees. So theta has to be less than or equal to 39 degrees. If I go over it, I'm going to slide. If I stay under it, I'm okay. You see how the inequality is going to work? We'll see, because I'm going to show you what I think you should be capable of doing. Let's see. Let's just see if you can. This is going to test some of your algebra skills, but I think they're due for a test. I know you guys are all Floridians. You lived here a long time. That this is what we call a sled. So it's a sled. All right. There's a 20 kilogram sled with a coefficient of static friction of 0.5 between the sled and the ground. You pull on the handle, which makes an angle of 30 degrees with the horizontal, and you apply a force this way. How much force is necessary to just start the sled into motion? I'm pulling it to the left. You ever pulled a sled before, or a wagon, or? Okay, so I'd say I'd put wheels on it, but I want there to be friction. So say the wheels fell off your wagon and you're just dragging it. So this is you. Help me, my wagon. Okay? And you're going to pull it this way. But you're pulling along the handle. So, do you have a downwards arrow? And what'd you label it? Good job. Way to go. Do you have another arrow? Name another arrow. Going directly upwards. I'm not going to make it as big as the weight, though, because I'm pulling slightly upwards on the handle of the wagon. So in trying to keep my forces as proportional as possible, I'm probably going to indicate that the normal force is going to be a little less because I'm also lifting upwards on the wagon. The normal force is what we call a responding force, responds to the situation. So if I'm pulling upwards, I make the normal force less. Anybody ever stood on a scale before and pushed down the counter or pulled down or something? The normal force responds to the circumstance. Now, I'm gonna have to draw something else. How about the handle? Is that a good one for you guys? A tension force? Something this direction probably. Not sure how big I should make that, but I'm gonna just draw something that indicates there's some tension. And you could have just put F pull or something. You just need a letter here. What you use here doesn't matter. You're just trying to make sure you're identifying the forces and differentiating them with some letters so you understand what they are. And finally, one more arrow, what's it going to be? So this way? That'd be silly. No, this way. Although I saw some people argue about it. I think this way makes most sense. So, friction. Again, this is a net force equals 0 problem. It's a first law problem because we find out how much force it takes to get it started moving, but it's not moving yet. Now, that's our free body diagram. Our next job is to do what? We need a coordinate plane over top of this. I think it's pretty clear that if it's not accelerating, putting my coordinate system this way so that it's lined up with the most number of forces possible makes the most sense. Because that means only one of these forces has to be resolved. It would be silly to put it in terms of the tension. Then 3 of them would have to be resolved. So this makes the most sense to me. And hopefully it's starting to make a little sense to you. I'm going to name this the positive x direction and this the positive y direction. And I'm going to put in here that this is 30 degrees because we made x horizontal and the angle is measured relative to the horizontal. I have one force that I have to resolve. So this will be tension in the x direction, and this is the part of the tension that's in the y direction. How many forces are in the x direction? How many forces are in the y direction? 3. So, net force in the x direction, I see 2 of them, friction and t cosine 30. So t cosine 30 minus friction equals 0. How many forces do you see in the y direction? 3. I see 3. I heard somebody say 2 a minute ago, but I see 1, 2, 3. So the ones that point up, make them positive. T sine 30 plus normal minus t cosine 30. Oh, what am I doing? Not t cosine 30. Weight minus weight equals 0. Getting ahead of myself. All right, that is all the force concept model can do. It generates relationships. We now have 2 relationships, and we're supposed to be figuring out what T is, the tension. I don't think I can get it from either one of these, can I? I don't know the frictional force. I don't know the normal force. But I'll remind you, we know more information. We know that the static frictional force is less than or equal to mu times the normal force. One of the things you're going to begin to notice about friction is that it bridges together the x and y direction. Now, still not straightforward. There's some work to do here. Now, I'm going to solve this for friction, t cosine 30. I'm going to solve this for normal force, weight minus t sine 30. Obviously, the normal force is less than the weight because we're pulling up. And this is telling us how much less it is. But now that I have this, I can substitute into my inequality. Right? Friction, normal. So let's substitute into our inequality. T cosine 30 has to be less than or equal to mu times weight minus t sine 30. Tell me you see what I'm doing here. I have a few folks I know are still full-blown lost, so let's look over here real quick. I'm taking this, substituting in for normal, and this substituting in for friction. This preserves my inequality and gives me something I can solve for t. Now, my problem with this is I think some of you can't solve this for t. And I know some of you are going to want to plug the numbers in right away. I would encourage you to solve this for t using standard algebra first, because most of your test is going to be symbolic manipulation. Putting numbers in there does make it easier for some of you. Learn to deal with the algebra. Now, I'm afraid some of you can't solve for t. I will tell you what to do. Distribute mu first. Do that first. Get rid of those parentheses by distributing mu. You can do the math. You all passed Algebra 1. Then you have to collect any term with t on the same side. So do so. All right, I've done those 2 steps. Do you see those 2 steps? Distribute first. This it breaks up that part with the parenthesis. And now you can move the term over that has t to the other side so that t's are all on the same side. And just basic algebra. The other day I was grading tests. Actually, this is yesterday. I took a picture of it. Luckily, I won't say whether it was somebody in this class or not. Yes, we have to do calculus, but this was on one of your tests. We see what's wrong there, right? Because that's not equal. They just, I guess, 1/2 cancels one of the 3's. So you see why I have concerns about asking you to do this when this was on one of your tests, right? That's why I'm doing all this algebra for you. Okay, just so we understand each other. Besides, for those of you who don't know why that's funny, it doesn't equal 3, it equals 4.5. What do you do next? How do you get t by itself? That's right, you collect the t. We're pretty close now. What's the last step? Oh, no, I'll do one more step. Get t by itself. Get t by itself. Go all the way. Because on your test, when I say come up with an expression for t, this is what I'm expecting you to come up with. Right? That's an expression for t. Don't expect you're going to get numbers. Numbers make you do your math easier. I get that, and there's an answer, but that's not the way the test's going to be. Come up with an expression. And the reason you come up with an expression is it gives you more options. I could ask what angle would be better. What angle could I reduce my tension with? There's all sorts of stuff you can do here to make what you're trying to solve for change or different. So an expression is going to be the standard. Working with numbers, yeah, that makes it easier, but the expressions are going to be the standard. Now, yeah, you could go ahead and put your 0.5 and your 20 and your 10 and divide by cosine 30 plus 0.5 times sine 30. You can put that in there if you're desperate to get an answer. That will give you how big the tension needs to be.